Okay, so this is going to be a quick summary of section 1.1. Kind of zoom in a little bit here. So we got some definitions. What is a differential equation? Well, it's just an equation involving derivatives of some unknown function. Here I have an example from physics, the motion of a body in free fall, right? So this says that the mass of the object, right, times the second derivative of the height of the object, right, is equal to negative the mass times the gravitational constant here, right? And so a lot of this you would discuss in a physics class, right? But we know that the acceleration of the object is the second derivative of the height, right? And so this is mass times acceleration. And since the only force acting on this is gravity, that's why the right-hand side is negative mg, where the negative sign comes from the fact that we're falling down, okay? Anyway, none of that really matters, right? Now we can divide by m. Now we have the second derivative of h with respect to t is equal to negative g. I'm going to switch notation, right, back to h double prime, which is also a notation for the second derivative, right, just because we're sort of more used to it. So h double prime is equal to negative g. So then if I want to know what h prime is, I just have to integrate, right? H prime of t will be the integral of negative g, which is equal to negative gt plus an arbitrary constant, right? I'm going to call this arbitrary constant v0 because it turns out to be equal to the initial velocity of the object, right? So now I have this nice expression for h prime of t. So if I want to know what h of t is, well, I'll just integrate again, right? And I get this and another arbitrary constant, h0, which is the initial height, right? And then there we have it. The h of t is right there. Okay, here's another example from physics, radioactive decay, where A of T is the amount of radioactive isotopes in some object, right? And what this is saying is that the rate at which the number of isotopes is changing is proportional to the amount of isotopes that we have. Because if there are more isotopes in the object, right, then there's more of a chance of them decaying, basically. And so we have that the rate is proportional then. Okay, how do we solve something like this? Well, it's kind of tricky. We divide both sides of the equation by capital A here. So then we have 1 over A dA dt is equal to negative k. Now, k is just a constant, called a constant of proportionality, right? So if we integrate both sides with respect to t, we get this nasty expression here, right? But that can be cleaned up a little bit. dA is really the same thing as dA dt times dt. So then this whole, maybe I'll circle it in blue here, this whole part right here is really just dA. Okay, and so that's how I get the integral of 1 over a dA is equal to the integral of negative k dt, which looks kind of weird because on the left-hand side, I'm integrating with respect to capital A, and on the right-hand side, I'm integrating with respect to t, right? I assure you this works just fine. You have to remember that a is a function of t, so really we still have functions of t going on the left and the right, okay? So now we have the natural log of the absolute value of a is equal to the negative kt plus c after integrating, right? So we can do e raised to both sides, exponentiate both sides. E and ln cancel off, so we have the absolute value of a is equal to e to the negative kt plus c, right? But here I use an algebra fact that anytime we have e to a sum, that's really just the same thing as e to the first thing times e to the second thing. And so I chose to write it this way: e to the c times e to the negative kt. Now, e to the c is just a constant, so I'll call that c1. But I'm going to make a special note that c1, while it's arbitrary, it's an arbitrary positive constant only, because we're taking a positive e, right? E is a positive number, and we're raising it to a constant c. And e raised to anything will always be positive, okay? So C1 is a positive constant. So we have that the absolute value of A, which is positive, is equal to C1, which is positive, times e to the negative kt, which is positive, okay? Now, if we drop the absolute value bars, right, that says that A could be equal to plus or minus C1 e to the negative kt. So then now, plus or minus C1, well, that's just plus or minus a constant, right? But now, plus or minus C1 is allowed to be a positive constant or a negative constant. So it's just some real number R. That's what this symbol means over here, that C2 is in a set of real numbers, right? So I'll call it C2. So then the solution there is A of t is equal to C2 e to the negative kt. Okay, so there we have it. We solved two differential equations already. Here's one more example from physics. Displacement of a vibrating string. This is wave propagation problem. So what this says is that and the symbol right over here means partial derivative. So the partial derivative, right? The second partial of u with respect to t. All right, so that means you're taking a derivative of u with respect to t twice, basically, right? Minus some constant c squared times the second derivative of u with respect to x, right? So here I'm taking the derivative of u with respect to one independent variable. Here I'm taking the derivative of u with respect to a completely different independent variable. So u here is a function of x and t, two different independent variables here, okay? And so that's why we have to use partial derivatives to indicate that this is a function of more than one variable, basically, okay? So what's going on here, what this is actually modeling is you can imagine a string, right? And you're kind of just shaking it up and down, right? Just shaking it up and down. And so you're going to get like peaks sometimes and valleys other times. X is the distance from the starting place, right? So here, if this is your X, then your point U of XT is down here, where this is just some snapshot at some time T, right? If you change the time, right? If you look 1 second later, the string is not going to look like this. Maybe this point will be up a little bit more, okay? I'll say that note that we use partial derivatives here, which are necessary anytime we have a function of multiple variables, right? Hence, we would not write straight du dx or straight du dt, but instead we write curly du dx and curly du dt. Okay. All right. So I'll make a note here that these partial derivatives over here make this problem way more challenging than solving one that has just regular old derivatives like the ones that we did above. Okay. So definition. If a differential equation involves a derivative of one variable with respect to another variable, right? Well, then the former variable is called the dependent variable, right? Like y of x. So then y is the dependent variable, right? And the latter variable is called the independent variable. Okay. A differential equation that involves derivatives of a function of a single independent variable only, like so y is a function of x only, let's say, right? That's called an ordinary differential equation. Okay. So up top over here, right? This is an ordinary differential equation because h depends only on time, right? The second example, this is an ordinary differential equation because your a depends only on time, okay? Now, on the other hand, one involving derivatives of a function of more than one variable is called a partial differential equation. So this last example we just did here, where we had these partial derivatives, right? Since u is a function of more than one independent variable, right? That makes this a partial differential equation, okay? Now, the title of this class is Ordinary Differential Equations, so that probably gives you a hint that we're only going to be talking about ordinary differential equations in this class, right? And instead of saying ordinary differential equations all the time, I'm just going to abbreviate it as ODE, right, for ordinary differential equation. And PDE is another common thing for partial differential equations, okay? All right. Okay, so another definition here. What is the order of an ordinary differential equation? Well, it's just the highest order derivative. So for example, dy dx equals xy, well, we're taking the first derivative, so it's a first order differential equation, right? Here we're taking the second derivative of y with respect to x, right? That's the highest order derivative there. So this is the second order differential equation. Now don't be tricked by part C over here. We're just taking the first derivative of y with respect to x, and then we're cubing that, right? So it's still a first order differential equation. It's not a third order differential equation. In order for it to be a third order differential equation, we would need to take the third derivative of y with respect to x, okay? Now, an nth order linear ODE. So this is just a special type of ODE. I'm not really sure why they threw this in the background section of section 1.1, but an nth order linear ODE has the following form. So here my an of x, an minus 1 of x, a1 of x, all the way down to a0 of x. Those are just some functions of x, some arbitrary functions of x. And then so is b of x over here on the right-hand side. And you can see that these are kind of like coefficients on the derivatives of y. Right, so here we have y itself, which I like to call the 0th derivative of y, because you're not taking any derivative of y. Right, here's the first derivative of y. Right, there's going to be a term over here for the second derivative and the third derivative and the fourth derivative, right? And we're adding all of these together. So it's a sum of these products, right? And so this is the general form of an nth order linear ODE. Okay, and so a second order linear ODE might have the following form, right? We have some function of t, let's say, times y double prime, plus some function of t times y prime, and then plus some function of t times y is equal to some function of t. Yeah. Okay. And for this particular example, I chose constants, but it can be functions of t if you want them to be, right? It makes them significantly harder to solve, though. Okay. Anyway, so that's the end of section 1.1.